Hi there, grade 12s. Welcome to Work, Energy and Power lesson. If this is your first time watching my lessons, please make sure that you hit the subscription button so you don't miss the next lesson. So we're going to answer this question. I've seen this question from some of the past papers, but let's work on this one. So they say that we have a rescue helicopter that is stationary above a soldier. Okay, so the soldier has the mass of 80 kg and is lifted vertically upwards through a height of 20 meters by what? A cable at a constant speed. So I'm just going to analyze. I think it's best if we underline that weight, constant speed. We can even highlight that because it's very important that we keep in mind that this is at a constant speed of what? 4 meters per second. I'm very sorry. So now the tension in the cable is 960 newtons, and they want you to assume that there is no sideways motions during the lift, so the air friction is not to be ignored, or they say the air friction is not to be ignored. Let's answer the following questions. State the work energy theorem in words. So the work energy theorem, remember, this says that the work done on an object, the work done on an object, the work done on an object. Okay, what can we say about the work done on an object by a net force? The work done on an object by a net force is equal to the change in the object's kinetic energy. It's equals to the change in the object's kinetic energy. Please just give them that definition. You'll definitely collect that 2 marks. Or you can say the work done on an object by a net force is equal to the change in the object's kinetic energy. So what we are trying to say is that the work done by the net force is equal to what? The change in kinetic energy. And we know that the change in kinetic energy, we can write this as K final minus the K initial. Right. It's fine. Let's work on this question. Let's go and collect that 3 marks. Draw a label free body diagram, and you need to show all the forces that are acting on the soldier while being lifted upwards. So I'm just gonna go and look at my soldier. So this is my guy, and then now which force are acting on this? You need to be very careful. Remember that if the question says 3 marks and this tells you that on your free body diagram you need to give them 3 forces. So let's go and indicate the 3 forces that are acting on the soldier. So we have a force acting up, which will be the force of tension, or we can say the applied force. Let's not say the tensional force because I don't think it's best to say the tension, but the applied force. So this is F applied, which is 960 newtons. This guy, there will be the force, the FG, which is acting upward, downwards. This is my FG. So far I only have 2 forces. Where is the other force? Let's go and ask the statement. Where is the other force? The other force has to do with what? Friction. The F friction is not ignored. So if we are lifting something up, where is the friction going? In an opposite direction. The friction always goes in an opposite direction. So this tells you that from this point here, we're gonna have another force going down, and we can call this the frictional force. So this will be F for frictional force. So I'm just gonna give them that free body diagram so I can collect my mark. This is my F applied going up, and then we have the weight going down. Let's call this FG. It's going down. Then we have the frictional force, which is in an opposite direction. So I'm just gonna use F. You'll definitely get all the marks if you give them in that. So let's see what we have on the next question. Write down the name of a non-contact force that acts on the soldier during the upward lift. A non-contact force. Okay, so we are saying that the non-contact force is going to be the weight, Fg, or someone can say the force of gravity. The force of gravity. That's one mark. It's something that you don't need to stress about. Né? The force of gravity of the man. So if we continue, let's see what do we have on the next question. I think this is the last question of this activity. Yes. So now on this one, use the work energy theorem. So first thing first, what is the work energy theorem? The work energy theorem is the work done by the net force is equals to the change in kinetic energy of the object. This is the work energy theorem. Use that to calculate the work done on the soldier by friction after moving through the height of 20 meters. So remember, we need to find what? We need to first find the net force. We can find the net force, or we can calculate the work done by the applied force, the work done by the weight, and also the work done by the frictional force. So there are many ways that you can use to do this. So I'm just gonna go with this one. I need to find the work done by what? I need the net work done. So I need to find the net work done by the applied force. So let's say the net work, how can we put this? The work done by F applied, then we need to add that with the work done. We said how many forces are acting on the guy? 3 forces. Applied force, the frictional force, and the Fg. So let's quickly work on that. So we need to also find the work done by Fg, and then we add that with the work done by the frictional force. Then we equate this to the change in kinetic energy. And the question wants us to calculate the friction after this guy moved through the height of 20 meters. Okay, so now remember the formula that we used to calculate the work done. Which formula do we use? So we can say this is there to find the work done by the F applied. This will be equals to the force applied delta y, because this is, we are moving up, this is a vertical motion, and then the cos of what? The cos of theta. Then if we do the substitution, the F applied, look at this, the object is moving up with a force of 960 newtons. So I'm just going to substitute that as 960 newtons. So let's put this and say this is 960, and then the displacement. So the displacement is given there as 20. So this will be 20, the cos of the angle between the force applied and the displacement. Look at this. If the displacement going up is 20, so this line is parallel to that line, which makes the angle to be 0. So please pay attention. If the force is moving in the same direction as the applied, if the applied force is in the same direction as what? As the displacement, the angle is 0. So the angle between the displacement and the applied force is going to be 0. So this will be the cos of 0. So I can come and substitute this on this formula. Okay. Let's quickly substitute this on the formula. This will be, okay. Okay, so this will be 960, and then it's multiplied by what? 20, which is also multiplied by the cos of 0 degrees. Then we need to add, what should we add there? We need to add the work done by what? The work done by Fg. The work done by Fg. Remember, Fg, it's equals to the mass multiplied by the gravitational force. And the mass of the soldier was given as 80 kg. So the soldier has 80 kg. Fg will be 80 times 9.8. So the force will be the force of Fg delta y, the cos of theta. So if we substitute that, what do we get? This is mg. The weight, it's mg. delta y, the cos of that theta. Let's substitute the mass, it's 80, and this is 9.8. Then we're gonna say delta y, the distance traveled, is given as 20. What about the distance? I'm sorry, what about the angle? Look at this. FG is going down. So FG is going down. So if FG is going down and the displacement is going up, this tells you that the angle, it will be, let me say I have my FG going down like that, and then we have the displacement. This is the direction of the displacement. This is delta y. So look at the angle. The angle is what? The angle is 180 degrees. So if the force is going in an opposite direction as what? As the displacement, just know that the angle between the force and the displacement is 180. So I'm just going to substitute that as the cos of 180. I hope you guys understand how we got that. This tells you that if we do the substitution, this will be equals to what? Let's see. This will be 80 multiplied by 9.8, then 20, the cos of 180 degrees. So we're gonna add this with the work done by the frictional force, equate this to the change in kinetic energy. So now, to make this simple, remember we just highlighted that this moves at a constant speed of 4 meters per second, the constant speed. So if this moves at a constant speed, this tells us that the change in kinetic energy is 0. Constant speed, the change in kinetic energy, that will give us 0. So I'm going to substitute this to 0. Right, I'm going to substitute this to 0. Then we can take it from there. Okay, grade 12, let me explain this because I owe you guys the explanation. Why are we equating this to 0? I think I owe you to explain why are we saying that the kinetic energy is 0. Remember, when we talk about kinetic energy, the kinetic energy, the formula that we use is 1 over 2m v squared. So this formula tells you that when something moves at a constant speed, the change in kinetic energy is 0. Let me explain why. Because the kinetic energy depends on what? Depends on the speed and the mass. So if the speed doesn't change, the kinetic energy cannot change. So look at this. Remember when we say the change in kinetic energy, which formula do we use to find the change in kinetic energy? So this will tell you, remember we say V initial, constant speed is telling you that the V initial. So if we say something moves in a constant speed, the V initial will be equal to the V final. Okay, so the constant speed means that V initial is equal to V final. Okay, so now this tells you that there will be no change. Why? Because if we say the key final, we minus the K, the kinetic energy initial. What do you get? Because they are equal. So when they are equal, if you subtract those two, you'll get 0. So this tells you that the work done on an object is also 0. The work done on an object is also 0. This is the work energy theorem. I hope you guys are happy with that explanation. So now let's continue with the lesson. So now to solve this problem, I'm just going to take everything here and punch it on the calculator. Let's see what we get. Let's start with this part. I'm just going to first put this one on the calculator here. Let's put this on the calculator. Okay, let me do this. Okay, I'm just gonna first put that one on the calculator separately, then we'll put this one also on the calculator separately. So now let me quickly get my calculator. Let's put this. So this is 960. It's multiplied by 20, and we multiply that by the cos of 0. So the cos of 0, what do we get? We get 19,200. So I'm just going to write this down. So this is 19,200. So now let's work on the other one. So this will be 80 times 9.8. Let's see. This is 80 multiplied by 9.8, and then this is multiplied by 20, which is the displacement. This is multiplied by the cos of 180. So the answer should be negative because of that cos of 180. So this is negative 15,680. So it's negative 15,680. We still have the work done by frictional force, and this is equals to 0. Therefore, if you subtract the 2, let's see what we get if we subtract those two. This will be 19,200. We're gonna subtract the 15,680. Then this gives us 3,520 joules. So the work done by friction, it's equals to negative. I'm gonna explain why I'm gonna go with the negative now. 520 joules. Remember, friction does negative work. Why? Because it moves in an opposite direction. It moves in an opposite direction, so it's gonna do a negative work. And that's it for this question. This is where the question ends. They said calculate the work done on the soldier by frictional force. So the work done on the soldier by frictional force, that's minus 3,520. Then you'll definitely collect all that 5 marks. Thank you guys for watching the lesson. If you really did enjoy the lesson, make sure that you hit that subscription button, and I'm looking forward, guys, to see you on our next lesson, where we're gonna answer another question on this is what we're gonna work on, activity 4.